Hello. In this video we're going to review shear and moment diagrams, and we're going to solve them using singularity functions. Consider a beam, cantilever support, with a uniformly distributed load, a concentrated moment, a concentrated load, located at various points along the beam. So let's call those points A through D, and then the total length of the beam we'll call L. And notice the important locations we'll call points A, B, C, etc. Now the first step in solving this problem is to find the free body diagram. After we find the free body diagram, we're going to solve for reaction forces. Then we'll write the load equation, Q of x, using singularity functions. After we have the load equation written, we can integrate and find the shear equation directly from the math. From here we'll locate several important points in the shear equation. We'll use those important points to graph the shear diagram. After we finish the graph, we'll write the moment equation by integrating the shear equation. Again, solve for important moment points, and finally graph the moment diagram. So let's get started. Free body diagram. Since this is a cantilever support, we need to find the reaction forces that will happen at O. And those points are, there is a concentrated force R1 and a concentrated moment M1. And I'm going to denote positive in the typical counterclockwise direction as we're solving this. I'm also going to find any equivalent forces. This is especially important if I have distributed loads. So I'm going to say there's a capital W that's located exactly in the middle of the distributed load. And I'll say capital W is equal to the lowercase w times the area under its curve. Since this is just a uniformly distributed load, that's just B minus A. Now I can solve for the reaction forces. I'm going to sum forces in the y direction, and I'm going to sum moments about the origin O. Summing forces in the y direction, I'll get R1 minus W plus F, and say that's equal to 0. Substituting in for the values, and I'll get that the reaction force R1 is equal to 400 pounds. Repeating the process for the moment, I'm going to sum moments about O, and I'll get W times its distance, and notice its distance is A plus B minus A over 2. In this case that's 3 inches, minus the moment because of the way I've drawn positive, and then the force, since it's up, its moment is in the same direction that I've listed as M1 positive. Solving for M1, plugging in for numbers, I can get that this is 400 pound-inches in the counterclockwise direction. The next step is to write the load equation. What I'm going to do is I'm going to start at the origin and move all the way to L, and as I cross important points, I'll look at the free body diagram and contribute each of those points to the load equation. So let's start at the origin. I'm going to have a moment. Now notice this moment, this 400 pound-inches, is not the correct direction to make the beam hold water. And so this is going to be minus M1. And then the singularity function for a concentrated moment has this notation. I'm turning it on when x is equal to 0. That's what the 0 is for. And the minus 2 just means it's a concentrated moment. I also have something else that happens at 0. I have a concentrated force. This time it is in the upward direction, so it's positive. And the value, the minus 1, means it's an impulse, which is what we give concentrated forces. Moving along the beam, the next important point is A, and located at A, I need to turn on a step. Step is x minus A, that's the location we're turning it on. Raised to the 0th power is the formula for a distributed load. Notice it goes on not just from A to B, but it's going to go on from A until the end of the beam and beyond. And so I need some way to turn it off. And to turn it off would be to do the opposite. So starting at B, I'll have plus W. That'll counteract the minus W. At C, we have a concentrated moment. So again, here's our to the minus second for the singularity function, and again it's turning on at C. And then we have a concentrated force in the upward direction located at D, and we use the impulse singularity function. The next step is to solve for the shear equation, and as this is just integration, I can do it directly. Integrating this first term, the rules of integration for singularity function, minus 2 just becomes minus 1. Minus 1 becomes 0, 0 becomes 1, 0 becomes 1, minus 2 becomes minus 1, and minus 1 becomes 0. So this is just strictly the definition of integration for singularity functions. Now, solving for important points. Let's consider the region between x is equal to 0 and x is equal to 2. For that region, most of the singularity functions will not be valid. All of these back ones here won't be valid. So I'm going to cross them off directly. And we only have two left. We have the moment that turns on at 0, and we have the concentrated force that turns on at 0. We'll talk about how to conceptualize why this is the case, but for now, whenever we see impulse in the shear diagram, we're going to neglect that term and say it doesn't contribute to the overall shear forces. If you want to think about it mathematically, that's because this singularity function is occurring only at x is equal to 0 for 0 width, so it doesn't really contribute. So x to the 0 is equal to 1, so this is just equal to r1. It's a constant from 0 to a. From a to b, I now have a new term. This w step function is now active, and so it's now expressed as to the first power, and I have a linear equation here. From b to c, I now am turning on w, and now I'm turning on the counteraction to w, and if I solve for this, I'll realize the x's cancel, and I'm left with again a constant. Notice there's nothing here that has x in it. So between B and C, I'll use this force, this diagram. Again, the moment doesn't matter for the shear diagram, although we need to keep it because it will matter for the moment diagram. But I can neglect it as I'm trying to find the regions. And then finally, between D and L, I have a concentrated force. And this is the value that I'd solve. I also could look back at the free body diagram and realize that this solution here is just equal to my R2 that I calculated earlier. Now, finding those important points. At x is equal to 2 and at x is equal to 0 and every place in between, the shear is equal to 400 pounds. When x is equal to 4, if I plug 4 in here, I'll get minus 200 pounds. This brings up an important point. Since I crossed from positive to negative somewhere in the regime A to B, or 2 to 4 inches, I need to figure out where it was that I crossed. So what I'm going to do is I'm now going to solve the shear equation and set it equal to 0 and solve for some x1 that defines the location of the crossing. So that's a simple process. I get 3.3, and that lets me know that V of 3.3, which is a new important point, is equal to 0 pounds. If I solve V where x is equal to 8, it depends on which side of the section I'm on. If I'm on the C to D section, I'll get minus 200 pounds. If I'm on the D to L section, I'll get 0 pounds. So I'm going to record both of those points there. Now, listing those as well as what I understand about what happens at the end, let's see, at V is equal to 0, when x is equal to 0, it's equal to 400 pounds. At x is equal to 2, it's equal to 400 pounds. There's the place where it crossed the 0 axis. When x is equal to 4, it's equal to minus 200 pounds. When x is equal to 8 from the negative side, it's equal to minus 200 pounds. But from the positive side, it's equal to 0. And because this is a free beam on the right-hand side, I also know that the shear at 10 inches is equal to 0 pounds. Now I just need to fill in the graph. There's a line, another line connecting, another, and another, and there is my shear diagram. Now what about the moments? This concentrated moment here can be expressed on the graph. I can draw it as an impulse that occurs right there. And there's another one that occurs right here at C, or where x is equal to 6. And we'll see how that affects the moment diagram. The next step is just to calculate the moment. It's just the integration of the shear. So again, I can go term by term. Minus 1 to 0, 0 to 1. Notice when I integrate from 1 to 2, I also need to have something that happens in the decimal place. And again, this is just the definition of how singularity functions integrate. Repeating for this portion, the concentrated moment now becomes a step, and the force, concentrated force, becomes a ramp. The next step is to solve for important points, so I'm going to repeat the process just like I did with shear. I'm going to consider 0 to 2. I'm going to see the equation that occurs, and this is now a linear equation. It's multiplied by x. From 2 to 4, I'll see that this is now becoming a quadratic equation. From 4 to 6, it looks like it's a quadratic equation, but if I look carefully, I'll see that this first x term, this x squared times minus w over 2, will be balanced by this x squared by positive w over 2. They'll cancel each other out, and this will actually be a linear section of the graph. From 6 to 8, I'll add the concentrated moment, and then from 8 to 10, I'll add the contribution because of the concentrated force. Going back and solving for the points, if I solve for m is equal to m where x is equal to 0, I'll get minus 400 pounds. Where x is equal to, I'll get positive 400 pounds. For that new location of 3.33, which I understood to be important, I'll get 667 pounds. Notice that's bigger than 400. But if I solve for x is equal to 4, I'll get 600 pounds. So I'll recognize that this 667 corresponds to the maximum, the local maximum of that parabolic shape. Now I'm back in the linear section. I'll solve for 200 pounds at 6 from the minus side, but from the positive side, I'll see that it's equal to 400. And finally, at 8 inches, I'll solve for the reaction forces, and I'll see that the moment there is equal to 0, and that'll continue on to the end of the beam. So listing these values again and plotting the points where x is equal to 0, there's m, x is equal to 2, x is equal to 3.33, x is equal to 4, x is equal to 6 from the minus side, x is equal to 6 from the positive side, 8 inches, and finally 10 inches. Looking at the graph as we go along, we recognize that the contribution will be linear in the first section, parabolic in the second section, linear in the third, a step caused by the concentrated moment, continuing at the same slope. Notice the slope here is equal to the slope here, and finally nothing incurring at this free end is free indeed. Now I have my full moment diagram. So the two of these, my shear and my moment diagram, give me the maximum moment, 667, and if I look back at my shear diagram, I can find my maximum shear.